Okay. Now let's continue our class. And in last class, we have learned almost everything about the flux, and then we derived the equation of Gauss law. Now let's review a little bit about what we have learned. So first of all, what is flux? In an intuitive way, we can say the flux of the electric field is kind of number of field lines. So the stronger electric field you have, the larger area you have more flux going through that surface area. And therefore, the electric flux can be calculated by a surface integral of E and dA. E, of course, is the electric field, and dA is the surface, or the small piece of surface. And please be careful, this is dot product for two vectors. When we talk about vectors, then we have to take care of the directions of the vectors. So for E, of course, the direction is usually shown in the picture. But for dA, we define the direction of dA to be the normal direction of that specific surface. And in a lot of cases, when we talk about the surface, we're talking about the closed surface, especially when you solve problems using Gauss law. So for a closed surface, then the direction of the surface is perpendicular to the surface, but pointing out. Then you do the dot product for two vectors, you will get the flux. And here is one example of calculating the flux for a point charge. In order to use Gauss law to solve the problems, what we need to do is we need to select or draw a Gaussian surface, and this surface usually need to be in a specific symmetric. For example, in this question, when we're trying to calculate the flux by a spherical Gaussian surface, the easiest surface we can draw is a sphere which is centered at the point charge center. And then it becomes a very specific. For example, the E at any position on this surface is the same in magnitude. Of course, the direction is different, but the magnitude is the same. And then at any point on the surface, the E, electric field, is always perpendicular to the Gaussian surface. When E is perpendicular to the Gaussian surface, that means E is in the same direction as your surface, because we define the direction of the surface to be perpendicular to the surface. So E and dA are in the same direction, then cosine theta equals to 1, then the dot product becomes EA cosine 0, which is EA times 1. And then it becomes E times A sphere, the area of the sphere. And then we all know how to calculate the sphere area, which is 4 pi r squared. And then we can calculate phi equals to, first, we can calculate the E here, which is Q over 4 pi epsilon r squared, and then times the area, which is 4 pi r squared. When you cancel out the 4 pi r squared, you get Q over epsilon, which is a flux. So it simply means the flux of a Gaussian surface equals to the net charges inside this surface. So here we use a point charge to derive the Gauss law, which is here, phi equals to Q over epsilon 0. This is the equation of Gauss law. We use a simple chart, single chart to derive Gauss law, but actually the Gauss law is a very general law. It can be extended to any charged system based on any Gaussian surface. It's not necessarily to be a symmetric Gaussian surface. Any Gaussian surface is fine for the Gauss law. But when we do calculations, usually we choose some symmetric Gaussian surface simply because we want to take advantage of the symmetric so that it makes our calculations easy. It doesn't mean Gauss law has to be applied to a symmetric system. It's not necessary. So here, the electric flux through any arbitrary closed surface surrounding the point charge Q is the same, actually. For example, if you have point charge here, you can draw different types of surfaces or closed surfaces. Those enclosed surfaces could be called Gaussian surface. As long as the Gaussian surface or the enclosed surface contains this charge, then the flux for such surfaces are the same. Because intuitively, let's see, intuitively, if you have a field line go through one surface, let's say the red surface, it must also go through the black surface. So you can imagine if this point charge is covered by and closed the surface, then all the field lines must go through that surface. Therefore, no matter which way you draw the enclosed surface, the flux for such a system, which is a single charge, should be the same. This is for a single charge system. If you have multiple charge systems, it's the same thing. For example, for the Q2 and Q1, it has some field lines going out. For some negative charges, it may have some field lines going in. But as long as you make a surface which is containing all the charges, then no matter which shape is the surface, the flux should be the same. And in Gauss law, phi, or the flux, equals to Q over epsilon. Q is simply the sum of all of the charges inside the Gaussian surface. So here is a formal equation of Gaussian surface. Flux equals to Q over epsilon 0. Okay, now let's do a quick check. Which option do you think is correct in this case?
The 20 on the bottom, which way is it pointed up?
Yes, it's going up. Let's say arrow is too small. Let's make it bigger. Oh, I forgot one thing. Are we recording? Oh, good, good. We're recording. That's good. Okay. Did you get your answer? So let's see who want to choose A or B or C or D. Okay. Now let's see. First, I want to ask a question. So let's see this number 15 and let's say 20. For flux, which one is positive? The 15 or the 20? The 15 going in or the 20 going out? 20 going out is positive, right? Okay, so that's the basic, let's say, that's the fundamental thing. If we define that the surface to be positive, if this, we define the direction of surface to be positive when it's going out, then let's say for the 15 number, it's going in. The field line is going in, but your dA, that's the direction of dA. We define the positive direction is going out. So dA is going out. Then cosine theta is cosine 180 degrees, which is -1. So it results in a negative number. So as a conclusion, when a field line is going in, it results in a negative flux. Going out means positive flux. Okay, then let's see the answer is outward. So net flux is outward, then your flux is positive. The easiest way is this is going in, this is going out, 15, 15 canceled. So going in 20, going out 20 canceled. Going in 50, going out 10. So the answer should be B, right? So the answer, I think the answer is wrong. Let's do it again. Erase pen. Okay, let's do it again. Now, this is going in 15. This is going out 15. So they canceled. This is going out 20. Here is going in 20, canceled. So here is going in 15, going out 10. So the net flux is going in. Then it's negative. It's a negative flux. So the net charge should also be negative. So this is wrong. The answer on the slide is wrong. Okay, now let's see this one. Which Gaussian surface has larger electric flux? Did you get your answer? Okay, now let's see. So who's going to choose A or B or C or D? Excellent. Sorry. It's misleading because when I take a look at the, it's very misleading. When I take a look at the example, I thought it's Q and Q. But actually, if you take a look at the charges, it's double the Q. So surface B have greater electric flux. Okay, since we're on this topic, now let me give you another question. Now you have a charge here, let's say Q here. Let me make a surface. So this is say a smaller surface. Now you have A, B, C, D. I'll say this surface is E. The smaller surface is E. And then let me make a big surface, the EF. Now you have three surfaces. A is the original surface, E is a small surface, and F is a big surface. They all contain the charge of Q. So my question is, which surface has a larger electric flux, A or E or F? They're the same? Right, excellent. Now let me give you another question. You have a Q, let's say here, and then you have a 2Q, double the Q. And then you have, okay, let's make it more complicated. It's a negative Q and the 2Q, and then positive Q. Positive Q is here. Now you have three charges. You have Gaussian surface A, B, let's say C, and then this is D. Now you have four surfaces, A, B, C, D. So which one has the largest flux? A, B, C, D. Okay, so now let's see. So who is going to choose option A or B or C or D? Okay, great, great, awesome. Okay, now let's have another test. Now you have a charge of Q, and you have a Gaussian surface here. You get the flux to be, let's say, phi on this surface.
Sorry, it was D.
Oh, okay. Now let's take a look at why the D has the largest flux. So the flux equals to, there are two ways to calculate the flux. First way, you do the surface integral of E dot product dA. So in this case, if you want to use this equation to do the calculation, you need to know the electric field at each point on the surface, and then do a surface integral. The second way is by using Gauss equation, use Q over epsilon. That's also the flux. So Q is the net charge inside the surface. So let's say in A, what's the net charge? Negative Q. In B, what's the net charge? Q, and in C, Q. So actually, the flux for B and C are the same, even though B contains 2 charges, C contains 1 charge, but the net charge is the same. So they will have the same flux. But for D, what's the net charge? It's 2Q. So D has the flux which is doubled than B and D. So D is the right answer. Now let's take a look at this example. Now you have a Q here, and you have a Gaussian surface, and you know, if you know the flux is phi, then okay, let's make it 2Q. So 2 times Q. The charge is 2 times Q. And then if I put a negative Q, a negative charge, which is 1Q here, then what happens to the flux on the surface? Is it going to be greater or smaller, or doesn't change? Doesn't change, because no matter what happens to the outside, if the net charge inside doesn't change, inside the Gaussian surface doesn't change, then the flux will not change, because flux equals to Q over epsilon. Q only means the net charge inside the surface. Okay, now let's take a look at this example. Which option is correct? Have you made your choice? Okay, so who want to choose A, or B, or C, or D? Okay, so they have same. As we said, if you have the same net charge inside the surface, then the flux should be the same. So apply Gauss law on some real examples. Gauss law applies only to a closed surface called a Gaussian surface. A Gaussian surface is not a physical surface. It might be a imaginary surface or theoretical surface. Then what you need to do is we need to apply Gauss law on those surface from some symmetry and superposition. When we apply some Gauss surface in a specific symmetry, the calculation could be very easy. Now let's see some examples. So first of all, let's take a look at this example. A spherical Gaussian surface surrounds a dipole. So the net charge, of course, for dipole is 0. Then which statement is correct? Okay, let's see. So who's going to choose A or B or C Okay, so seems like it's complicated because the three options are chosen by different groups. First of all, let's make a distinguish between electric field and flux. So what is electric field? Electric field is the field lines. For example, if you have some field lines like this, can we say the electric field is zero? No, because there are some field lines. So the electric field is non-zero. However, if the electric field line going out is, let's say, E, going in is negative E, then we can calculate it by using EDA. We can calculate the flux. The flux might be zero, even though there are some electric field going in and out, but the electric, let's say flux, the flux of electric field could be zero. Then let's take a look at the answers. Here you have negative charge, positive charge. The electric field is distributed in this way. That's the distribution. So the electric field is non-zero. It's stronger when it's closer to the charges, and it's weaker when it's getting further. So it's non-zero. However, if we ask what's the flux is zero. Flux means the total number of field lines going out. So because it's in a symmetry, so if there are, let's say, many field lines going out, you have the same numbers of field lines going in. Okay, now let's see this example. Which one do you think is right? Let's see. Have you made your choice? Okay, so who is going to choose A or B or C or D or E? Okay, so first of all, the answer is C, but let's double check. So now the flux is shown in, let's say, surface 1 and surface 2. And this, for this surface 2, it gets 2q epsilon 0. For the surface 1, it's q over epsilon 0. Means the flux for number 2 is greater or doubled compared to the flux of number 1. This is number 1. So flux equals to q over epsilon. So that means the charge, the net charge inside number 2 is doubled than the net charge inside number 1. So the charge inside number 2 is Q1. It equals 2 times the net charge in epsilon number 1. The net charge in epsilon number 1 is Q. Oh, I see. So there's a mistake. So let's say this is Q. Which one is Q1? Let's say this is Q2. This is Q1. Okay, now I understand why you're some of you are choose B and others choose C. Let's say if this is Q1, this is Q2, and then Q1 plus Q2. Q1 plus Q2 is the net charge in the surface 1. It's half of the net charge in the surface 2. So it equals 2 times Q1 plus Q2. And then you will get negative Q1 equals to 2 Q2. Then Q1 equals to negative Q1 equals to negative 2 Q2. So so one possible solution is C. So when Q1 is 2Q and Q2 is negative Q, then Q1 equals negative 2 times Q2. But there are some issues with the questions, with the problem. So it's fine. But you know what we're talking about? We're talking about it simply want to demonstrate that the flux is simply calculated by the net charge over a constant. Okay, now let's take a 5-minute break and then come back. I'll first pause this video recording. Okay. That's not our slide. Here is our slide. Okay. Outside the sphere of charge. Now here, let's say we have a sphere of charges. Let's say this is a sphere and it's uniformly charged by some charge density. So the charge is uniformly distributed in this sphere. So can we calculate the electric field outside this sphere of charge? And the answer, of course, is yes. It's similar to the point charge. For point charge, we know we can make a Gaussian surface, which is centered, which is a sphere, but centered at the point charge. Now, in this case, let's still make a Gaussian surface. It's a sphere. It's a sphere surface, but it's centered at the center of this sphere charge. So that what you can get is at any point on the surface of your Gaussian surface, E, the magnitude of E is a constant because they have the same distance from this charge. It's in a perfect symmetry. So E should be, actually the magnitude of E should be identical on any area of this surface. And the direction is always going out, which is perpendicular to this surface, which is which is shown here. And the direction of this surface is dA, shown here, so they're in the same direction. So theta between them is 0. So dA and E, they have an angle of theta equals to 0 degrees. Therefore, cosine theta equals to 1, because cosine 0 is 1. Therefore, E dot product dA becomes E times dA without vector. It's becomes scalar E times scalar dA times cosine theta, which is 1. It becomes scalar E times scalar dA. And then when you do the integral, E is constant, you can take it out. Then it becomes an integral of dA, which is the surface area of the sphere, which is 4 pi r squared. Then what you get is phi equals to E times A. So originally it equals to, okay, let's break it down. Originally it's E, dA, the all vectors, and then you need to do the surface integral. And then it equals to surface integral of E, this is scalar E, dA, scalar dA, cosine theta, and cosine theta, as we discussed, it's 1, so it can be ignored. Then it becomes E and dA. E is a constant, you can take it out, and then becomes the integral of dA, which is the surface of A, which is A surface shown here. Then 4 pi r E. Q, actually, the flux equals to 4 pi r E, and also flux equals to Q over epsilon 0. Then 4 pi r squared E equals to Q over epsilon. Then if you want to calculate E, you just take 4 pi r squared to the other side of the equation. You will get E equals to 1 over 4 pi epsilon r squared times Q, of course. And the direction, so here you calculate a vector. The direction is always in the radially outward direction. Let's use r hat to stand for a radial unit vector. So that's the way of solving electric field lines or electric field outside a spherical charged distribution. Now let's see another example. Electric field of a plane of a charge. So first of all, let's say you have a plane. This plane has charges, and the charges are uniformly distributed. Let's say you know the charge density on this plane. Can we calculate the electric field, let's say outside this plane? Okay. First of all, we still can use Gauss law or make a Gaussian surface to solve the problem. Let's say if you have this plane and you want to calculate the E at this moment, at this position, what you can do is you can make a cylinder in this way. So first of all, the cylinder, at the ending surface of the cylinder goes through the point that you want to do the calculation, which is here. And then the side surface of the cylinders are perpendicular to your surface. And on the other And let's make a same distance between here and here. So in this way, you make a symmetry cylinder, which is cut by this plane. Actually, it's cut by this plane at the middle point of this cylinder. So that in this way, we can use Gauss law to do the calculation easily. Then Gauss law tells us the flux equal to E dA, which is the dot product, equals to Q over epsilon 0. Okay, so the right side is easy. On the right side, epsilon 0 is a constant. So what is Q? Q is the charges shown on this small piece of surface. Let's say it's dA, because here, if we define here is dA, then the surface area is dA. So the Q, let's say Q equals to dA times the density of the charge. Let's say if the density is eta, that's Q. So the difficult part is on the left of the equation, E dot dA and surface integral. So on the cylinder, we can divide the cylinder into 3 pieces of surfaces: the left end, right end, and the curved side surface. So first of all, are there any field lines go in or go out the side surface? No, because you can imagine the electric field lines should be perpendicular to this plane. And if the cylinder is perpendicular, then there's no field lines goes in or out of this side surface. So there are only field lines goes out of the surface at the right and goes out of the surface at the left. And the E on the left side and the right side should be the same magnitude but opposite direction, because we made a symmetry here. And then E at this surface should be a constant. And the direction of E is the same as the direction of A, dA. Therefore, your phi, let's first talk about the right side. The integral of your E times dA becomes the integral of a scalar E times scalar dA times cosine theta. Theta is, of course, 0, then cosine theta is 1, so it's canceled. Now E is constant at this surface, so E can be taken out of the integral. It becomes E times phi, surface integral of dA. The surface integral of dA is, let's say, just this area A. It's A, if we define it to be A. And then on the other side, it's the same thing. And the E on the left and the right, it should be the same, but in opposite directions. So what you can do is, finally, you will get, this is the EA on the right, and then you have EA on the left. So for the total flux, you have 2 times EA, that's total flux. And then for the charge, you have, sorry, this is a surface integral of dA and epsilon on this middle surface on the plane. So finally you get A eta. So this is the Q. So Q is A times eta, and the flux integral equals to EA but times 2, because you have 2 ending surfaces. So finally, you have 2EA for the flux, and you have eta times A for the charge, then phi equals 2EA, which equals to Q over epsilon 0. And Q equals to eta A as we calculated. This is Gauss law, of course. And then when you calculate E here, you have two, you have A here, A and A, they're canceled. Then E equals to just eta over 2 epsilon. So that's the solution of electric field on the side of the plane charge. Okay, do you have any questions for this calculation? Okay, good, good. Okay, if you have no questions, let's see this quick check. So which option is right? Now we're talking about the flags on the two flat end. What's the flags? So who's going to choose A or B or C or D or E? Okay, so this is a line of charge. So in our previous example, that's a plane of charge. So the electric field are quite different. The electric field in this problem is something like that. But in this problem, what's the direction of the electric field lines? Going out, right? So when we're talking about the two flat surfaces or the two ends, actually all of the field lines, they are parallel to the two ends. So no field lines will go in or go out of the surface. Therefore, it's a 0. Does that make sense? When the charge distribution is in this way, then your field line is simply going in a radial direction. So when you cut it perpendicular to the line, then there's no flux. Okay, now the flux through the wall, which is a curved surface, is that 0 or non-zero? Now we're talking about the flux on the side wall. Will that be 0 or not? Are there any field lines going out of or going in through this? Yes. So it will be a positive number. Okay, conductors. Let me see. Let's leave conductors for next class. So that's all for today's class. So in next class, we're going to introduce the conductors, the effect of conductors in a electric field, and then we'll start our new chapter, which is chapter 25,